Yeah, so let's start.
And the question, I will speak about the goal of this lecture is to tell what is sample complexity. So how many, if you have a classification problem, how many, what's the size of the training set you need to train a good classifier? And first I will speak about qualitative problem. So if we have a problem, can we do it with finite amount of data? It's the start. And then after we answer this question, then we will think about how much data. If the answer is finite, how much data do we need? So first step. So let us think about a very easy way to measure how good is a classifier. So, well, let us, even before this, let us say what is risk of a classifier. So all of the lecture, I will talk about binary classification. And so a classification task consists out of a distribution. So out of two things, we have a measure, we have a true classifier. Which maps inputs to outputs, and we assume that there is some measure P over inputs. And the question, and so if we have a solution F, then F, we say that a classifier, if F is the output of some learning algorithm, then we say that F is good if it has small risk. And it's just the risk of F is the probability that a test point is badly classified. Okay. And so when is the risk interesting? Since we have binary classification, risk is interesting if it's smaller than 1/2. Because it's very easy to find a classifier with risk at the most 1/2. So risk of the constant function 0. So imagine that y is equal to -1 and +1. Then we have two functions. One maps to the constant -1 and the other +1. And the risk of the function x that goes to first constant. So one of these constant classifiers has risk at most 1/2. And so it's clear why, because risk of the first constant plus risk of the second constant is exactly equal to 1. Because with probability 1, exactly one of them is correctly classified. Okay. So now, this is this doesn't take probability over training into account. So a better way to check how good our algorithm is for this particular task is to first generate training set, and we will use the same measure P for training and testing. So in all this analysis is the basic assumption, the same measure is used. So so there are 4 steps in our testing procedures. So in the first step, we collect the training set S over Pn. So we take n independent sample and n independent inputs according to P. So we have x. So we have S equal to x1 till xn. So we pick them independently. Then we will ask supervisor for the true labels. So we don't have access to the true classifier, which I usually write as H. But we ask for the labels, SH. And this is just x1, H of x1. We transform the unlabeled set to a labeled training set, x1, H of xn. Then we give the label set to the learner, and the result is a classifier. which I denote FSH. Then we generate a test point according to P. And then the measure of performance is probability that the test point is wrongly classified. So here we have three sources of randomness. First source is the selection of the training set. Last source is selection of the test point. And we allow for probabilistic algorithms. So this also has randomness. This is a deterministic step because H and P are fixed in the problem. So the things that are fixed here are H, P, and N. So once we fix these three things, we've specified classification problem, and we can measure the performance. Okay. So that's our performance. Now let us make some observations. Performance is only interested when it's smaller than 1/2. For the same reason, we can take the learner that just picks constant function with probability 1/2, each of the two constant functions, and it will obtain, this probability will be exactly equal to 1/2. We are also happy if this is close to 1. Imagine that this is close to 1. Then we also have fixed our learning problem. Because
So take the opposite.
yeah. So we modify our learner, indeed take opposite. Okay. So let's do a small example to evaluate this measure. It's just a very naive way, I think the most simple way to measure the performance of a learning algorithm on a certain task. So this is not in any other books, but it's all the time implicit in various proofs. So that's why I decided to speak about this measure. So if we speak about it, then all proofs like vanish and become non-technical. That's why I speak about it. Okay. Yes, let's do a small example. Let us consider X just containing 3 points. I will change the marker because otherwise it's not visible on the camera. -1, 0, +1. Let's say Y is equal to 0 and 1. Let's consider the nearest neighbor algorithm, and P is uniform on X. 1 nearest neighbor. Classifier. And let us put n equal to 2. So a training set of 2 elements. And then the question is, what is the value of this thing?
And what is H?
Sorry, good point. H is equal to x squared. That means, so here is x, we have -1, 0, and 1. And so the labels are 1, 0, 1. So I will help a little bit. So note that, so the training set consists out of 2 points. Whatever are these 2 points, there is always 1 point that's wrongly classified. So to see it is considered 2 cases, either 0 is in the training set, then one of the 2 neighbors of 0 is not, and it will be wrongly classified.
Sorry, what do you mean by 1 nearest neighbor classifier?
Yeah.
I mean, is it the way we train the model, or?
Yeah. So the output of the nearest neighbor algorithm, it will look to the point. So given x, it will look to the closest input to x, and then output the same label. So imagine the training set consists of -1 and +1. And then we ask for point 0. Then it will predict the label 1. If it is -1 and 0, and we ask for the label on +1, then it will predict 0. Okay. And so to help with this, to evaluate this, so maybe it's more clear if we write it as an expected value over S, and of the probability that X of the risk. Okay, and I claim that this is always at least 1/3. So this is 1/3. Actually, it's always 1/3 or 2/3. It cannot happen that all three are wrong, because the training set always contains at least 1 point. So the training set can have 2 times the same point as possible. Risk 1 is not possible. Risk 0 is not possible. I just explained why. So that means one of these two must be the values. And now, where can we make? There is only one way to make 2 mistakes. So what should S be to have 2 mistakes?
Only 0.
Yeah. Yeah. So when S is equal to 2, S is equal to 0, 0, then there are 2 mistakes, because this is wrong and this is wrong. But in all other cases, we will have 1 mistake, because all other cases contain, if a 1 is present and another point, so if the points are different, then it's okay. If we have 2 different points, we have 2/3, 1/3 risk. Yeah. So if we have 2, and in the other case, we have 2 times this point or this point, and then one of the 0 will be wrong and the other will be correct. So this is equal to 8/9 times 1/3 plus 1/9 times 2/3. So it's a little bit more than 1/3. So it's 27. Okay. So that's our example. But now we have a definition of performance of learning algorithm. It depends on P and H. H, the true classifier. So we are in the realizable setting. Every input has a true label that we use for training and testing. But now what if we want a definition that does not depend on H and P, but maybe on N, the size of the training set? What can we do? We are interested in worst case performance bound, so let us take the supremum of this thing. Let us use this as performance measure.
Supremum over H.
Over all H and all P. Let me write it. And that's supremum over H and P. So measures P, H from X to Y, and measures P. So let us use this performance measure. Now I claim that there is kind of problem. So if we use this performance measure, then the best learning algorithm is just a learning algorithm that remembers the labels from the training set and outputs when it gets an input from the training set. So for this, we need to prove some lemma. And the lemma I will write here in another color. So the lemma says that the best possible bound we can achieve is obtained by random guessing on unseen inputs. So there, here it is for all learners. So for all measures P, there exists a true classifier H such that the probability over, so this probability is at least 1/2 minus the probability, so it is 1/2, 1 minus the probability of seeing a test point that's in the training set. Here is the same probability from this definition. As h of x not equal to h of x. So we achieve equality if we just remember what is in the training set. It's easy or difficult to understand this lemma. So I'm saying that there always exists a bad function on which the learning algorithm is as bad as just, here is the probability that x is not in S. So the performance is just as good as random guessing 1/2 on unseen inputs. So if you're always good on seen inputs, then you achieve this with equality. And so the proof is rather, it's not so difficult. Let us go to the proof. So proof goes by probabilistic method. So we will fix, so to find h, we we generate h probabilistically. And then we will look at expected value of this. We will prove it for expected value over the way we generate h. So we will prove that this is true for a random h. So let us fix a learning algorithm, measure, generate this probabilistically, and additionally let us now fix S and some x not in S. And let us look to the probability over the generation of H that FSH. Okay, I need to tell you how we generate H. For every, we take a random H. So for every input, we pick one of the two labels randomly and independently from all previous labels we picked. So then I claim that probability over H that we are wrong is equal to 1/2. So that's just by definition of H, or generation process of H. So here we have something that only depends on the training set, and we fix x outside the training set. So when we generate this label, It is independent from the training set and hence on what the learner produces. Learner only depends on the training set and its own randomness. So these two are independent, and this is uniform probability, 1/2. Yes, comment. So this is equal to 1/2. And this is for every S and X not in S. So now let us take expected value over S and X. So then expected value over S in P and X, S in Pn and X in Pn of probability over H, F. Okay, let us write this as star. Star. So for this expected value, we consider two cases. Case where X is in S and X is not in S. So this is equal to probability that X is in S times probability of star given X is in S plus probability X is not in S, probability star of X not in S. Okay, and now this thing, let us drop the first term, let us drop this one, so we get an upper bound, a lower bound I mean, and we know that star, probability of star given X is not in S, is precisely this probability. So this is equal to 1/2. So we have that this is equal to probability X is not in S times 1/2. And here probability goes over generation of H, X is in P, and S is in Pn. Okay, and now I claim we are finished. Because here we have a probability, and here we have expected value of a probability. But expected value of probability is just probability. So we have proven that this is at least this. So note that I take the complement. 1 minus probability X is in S. Here I have X is not in S times 1/2. So this lemma is proven. Okay, so this lemma tells us that with this performance measure, we do not better than trivial learning. Well, it can be good if our training set covers all possible inputs. So if we have a very small input space and this probability can be made very small, okay, then we can be happy. But typically, our input space, for example, are bit strings of length d, then the size of X is exponentially large. And that means if the distribution is sufficiently smooth, this will be exponentially small. And so we will get that our performance is close to random guessing on some bet H. So this is called, well, there are many variants of these results. They're called no free lunch theorem. And so it's called like this. So the proofs follow this. So I gave a very simple case of no free lunch theorem. They can fill many pages with the proof, but they have all the same structure as I just gave. It's very trivial. Sorry, what do I tell? Yes, it tells us that if we want to speak about worst case performance, we need to restrict it through functions. Otherwise, there is always a bad one. So we can always think that what happens if nature is produced from random noise, then there is nothing to say. So we need to restrict H, and that's why we need a hypothesis class. In online learning, we had the same thing. We had hypothesis classes all the time to prove performance bounds. Otherwise, we could do something similar. Okay. So from now on, we will always have a set H of classifiers. The mappings, sorry. And we always assume that it's non-empty. So I will not say each time that H is non-empty. So when you see H, you should remember it's non-empty. Okay, the same for X and Y. Everywhere in this course, when X and Y appears, it's non-empty. Okay. What else do I need to know? I promised to tell you a qualitative definition. So now for each H, we have a more general classification. We have the task like, can we learn every true function in H? So this question, how can we turn it into mathematics? We said when we take the supremum over all H here, then it does not give us anything meaningful. It turns out that the whole theory works if we just restrict this H to a class H. If we say this is H. So then we can, all our interesting proofs appear if we look at this qualitative measure. So, when do we say that a class is learnable? Class is learnable if this quantity becomes arbitrarily small if the size of the data set increases. So this is our important definition. So I will call it learnable on average. So we will say H is learnable on average if the limit of this thing is equal to 0. So that's the definition. So now is the question, which sets are learnable on average? So there are some counterexamples. If X is infinite, and H contains all functions on X, then it is not learnable on average. This is, we need some work for this. It's a lemma, it's in the seminar, or the homework, I think. I forgot what I put in as first homework question. So, and for this, you use this lemma. So the plan is that you come up with bigger and bigger sets, you take the uniform measure to keep this bounded, and then you prove that this limit remains bounded away from 0. So you only need that X is infinite here, and then you can do it. So the measures P will be uniform on bigger sets. Okay. Now let us look to classes that are learnable on average. I claim that if H contains only one classifier, so 0 is not possible. But if H contains only one classifier, then it's learnable on average. So here, sorry, if there exists learning algorithm, if there exists a learner for which this is true.
And X is finite.
So X can be anything. Input space can be anything. And I claim that if there is only one classifier in H, then this is equal to 0. And so why this limit is equal to 0? Actually, if we fix any n, it's equal to 0 already for n equal. So it's a very simple learning algorithm. What should it do?
Repeat what H says. So it should be equal to H.
Yeah, so what is the output of the learning algorithm is a classifier. Yeah, it should always, output label H. So it should output a classifier so that just a unique classifier that's here. It should always, so it's it needs to see 0 inputs. It already know the answer. So even for n equals 0, this it can ignore its input. Okay. Now let us look to H equals two classifiers, f and g, and for all x, f differs from g of x. So, so I claim that this is also learnable on average. So if we fix n, how big is this value? Let's say n is positive, n is non-zero. What is a learning algorithm and how much can we get for the supremum? So here we have two functions, they're always different. Let's say the two constant functions, for example. So then, learner is also easy. As soon as it receives one example, it knows which function is true. So H belongs to here. It sees just one example, and so it can output the corresponding function, and this error probability will always be 0. So then it's also easy. Now the next case is if H contains two functions, but there is at least one input where the functions coincide. So now we have two different functions. F is not equal to g on some input, but there exists an input such that f of x equals g of x. So in this case,
so if the number of such x is finite, then it's 0.
So if the number of such x is at least 1, so there exists at least one input where the functions agree.
Yes. And if that,
In this case, this probability will never be equal to 0. Or let's say the supremum will never be equal to 0. And so what's happening here? So let us consider an example. So I claim that this probability is non-zero. What can happen? So there are 2 points. Here f is equal to g, and here f is not equal to g. And let us put probability, let's say that p is uniform on these 2 points. There can be more points, let's not care about them. But imagine there are 2 points like this. Now it can happen that that the learner receives all test points where f is equal to g. The training set contains all copies of this point. But then when the test point comes, it is probably equal to 1/2 with this and equal to 1/2 with this. So we cannot make it 0. We have to think about case, or maybe there can other probabilities, like this can be 0.9, and this can be 0.1, for example. Then if you get 10 points, with high probability, they're all here. With a reasonable probability, they're all here. But the test error will not be 0. So this will be positive. But still, in this case, I claim that the limit goes to 0. And so let us prove this. So, and for the proof, I will first tell a story. So about Middle Ages. So about the king. And king, some morning receives present. It's a big bowl with candy, favorite candy. He really wants to eat this. And it comes from political friend. But then in politics, you never know whether your political friend wants to do you a favor or wants to kill you. So in barbaric times where politicians killed people by poisoning, so it was a common problem of the king, and so he had food taster. So here is king, and here is food taster, and the food taster, so the king decides to do the following. He gives n random candies to the food taster, and if the food taster does not get poisoned, then he takes one random candy and he eats himself. And now is the question, can we bound the probability that the king dies? So we don't know which fraction of the candy is poisoned. Like if they're all poisoned, it's not like opponent, the political friend knows that there is food taster. So he will just put some fraction of poisoned candies. And so the king doesn't know what is the fraction of poisoned candies. So can we make a bound that works for all fraction of poisoned candies? And so the king wants to make a proof, and idea is as follows. So let me repeat. Food tester gets n random candies, king takes one random candy. So let's now think that the king takes n plus 1 random candies and then splits this in 1 candy for him and n candies for the tester. And then he gives this to the tester and he eats this, and afterwards, if everything is safe, he eats this one. So nothing changes. So in the first case, you see it's equivalent, right? So in the first case, n candies are taken randomly by him. He trusts the food tester. Well, king takes n points random, n candies randomly given to the tester. Then king takes one more for him. Let's now first take n plus 1, randomly shuffle, and then take 1. It's the same probability. Okay, now let us look to these candies. So I will mark poisoned ones with a cross. So what's the only way if we look to these candies? If there are 2 poisoned candies here, then we know for sure king survives. Right? Because he takes only 1. So then the other poisoned one goes to the tester and he dies first and king is happy. Well, maybe not so happy, but he needs new food taste. But let us assume it's minor problem for king. If there are 0 poisoned candies here, then the king is also happy because he cannot die. So we look at here the stage where there are n plus 1 candies. So the only way for the king to die is if there is exactly 1 candy here. There is exactly 1 poisoned candy. But then what's the probability? If there is exactly 1 poisoned candy, what's the probability that this goes to the king?
1 divided by n plus 1.
Yeah. So probability that the king dies is bounded by 1 plus n. Okay. Now let us go back to our question. So we have two classifiers, f and g. And now we need to bound the probability that a test point is misclassified. How do we connect? The learner algorithm will work as follows. Learner will always pick f unless the training set contains input-output pair that contradicts f. Okay? So that's the learner algorithm that we will use when there are two functions. Okay, now let us evaluate this supremum. So this becomes a maximum over two possible true functions. If f is a true function, then there is never a mistake, because the training set will never contain an input-output pair contradicting the f, the true function. So what if we pick g as true function, then there can be a mistake. When does it happen, this mistake? If the training set S contains all points that are consistent with G, but the test point is inconsistent with G. Inconsistent with F. So the training set has no inconsistent points, and X is an inconsistent point. So how do we translate to the candies? So of course this is the set X. What is poisoned candy? It's inconsistent. Yeah, inconsistent with F. So the candy that goes to the tester is the training set. And candy that goes to the king is test point. So the only way to realize this event is if the tester gets a training set with all good candy, and the single poisoned candy goes to the set. So in this case, so if we take away the limit, so let us think out the limit, then we see that this is bounded by n plus 1. So when we place the limit back, we see it's bounded by limit for n of infinity. N goes to plus infinity, this becomes 0. So when we put the limit back, we see that this class is learnable on average. Okay, so that's our small lemma. If h contains two functions, it's learnable on average. Now, what about finite h? It's also learnable on average. So how can we change the argument? So let us take the limit back. And do you have an idea of what we can place, how we can modify this bound? First, what should be the learning algorithm?
Perhaps we output the first function, then after each well, we arrange the functions in sequence.
Yeah.
And then output the first function. If we make a mistake, we take the next function.
Yeah. If the training set contradicts the first one, we go to the second one.
Yeah.
If it contradicts again, to the third one, and so on. Exactly. Okay. And now we want to bound the probability that the test point is wrong. So how can we do it?
Maybe we can randomly shuffle this sequence of functions. So with probability 1 divided by the number of functions, we guess true.
Why isn't the argument the same?
Yeah, argument is the same, but you need something extra because now, okay, what is the poison candy? So, different ways.
Well, it's perhaps it's we only think that there is a poison candy if oh,
So what we can do, well, we can. There are several solutions. So there is a true function, and then we can look to all the functions that come before the true function. So what can be the problem is that one of these functions coming before the true function is consistent. So on the training set is consistent with this true function. So it is. So if there is just like here, we have just one function that goes in the front, and so we have one bad event. But if we have f1, f2, f3, for example, and here is our 4 equals to h, then we have 3 possible problems. Right? And so we can use union bound to bound. So there are 3 bad events. Training set is consistent on f1. So f1 and f4 are consistent on the training set. f2 and f4 are consistent. f3 and f4 are consistent. And each event can be bounded in the same way, as if the others don't exist.
So the real bound is
Yeah.
the size of x?
Yeah,
h.
the size of h, and we can do a little bit better.
Minus
-1, yeah. Because in the worst case, the last one is a true function, and then h minus 1, many problems. Or you can translate and say that there are h minus 1 types of points in here. And then think, okay, now there can be more poisoned candy, but if n is large enough, it will go to 0. So if h is finite, then it's learnable on average.
could you repeat, please, the argument with f1, f2, f3, f4?
Yeah. Okay, so imagine h contains 4 functions.
Yeah.
And imagine that the last one is a true function. Then our algorithm might output something wrong if f1 is consistent with this one on the training set. But this
Okay.
probability, yeah, is at most 1 over 1 plus n. But then, if this doesn't happen, we can still have a problem with f2 and f4. Right? And then f3 and f4. So we have 3 times this error. Okay. So it's called leave one out technique to bound the error of the learning algorithm. And it's very convenient for SVM. It's for seminar. In SVM, there are, it's very easy algorithm in the realizable setting. In the separable case, it will look for a plane that separates positive and negative, and for which the margin is the widest. So for which the distance to all points is maximal. And it turns out that this algorithm only depends on a few points. So if we apply leave one out technique, then we add one more point in the training set and take it randomly out. And with high probability, it will not change the decision rule. And that means that this point will be correctly classified if it's transformed to a test point. Okay, it's for seminar. You will speak about it. Okay, and that's how you can, so I told you, I promised you in the course that we would explain,
So the perceptron algorithm find some plane and SVM algorithm finds the optimal plane.
Yeah. Well, perceptron actually in the limit, if you keep repeating the data set, it will find optimal plane. Oh, sorry, no. Yeah, you're right. It finds some plane because then it stops updating. Yeah, but there is margin perceptron algorithm, and yeah, it's sorry, my mistake. Okay, so now you learn there is one more remark. So here we had limit of n to infinity for learnable on average. And then you say, why do you put, so there are three operations, limit, supremum over h, and supremum over the measure p. And so why do you put order, limit, supremum h, supremum p? What if I put one supremum here, or both supremums here? And it turns out it's still, well, if both supremums are here, then rate of convergence can depend on h and measure p, and in this case, this definition is useless. Almost everything is learnable. It's almost always goes to 0. And then there is one case where you take supremum over p, but h you put here. You get non-uniform convergence. And this is when we have bounds that depend on the complexity of the classifier. Then we allow if h is, so here we can have very complex classifiers, whatever, half spaces with without margin, it works. But now if the margin is very small, then we will need more and more samples. No, I'm saying nonsense. It's not a good example. I'm contradicting myself. But let's say neural nets, then I think you can have, I should think a bit more, but these non-uniform bounds, they're also discussed in like important books. Okay, so that's all for qualitative measures. So we have two interesting ones if we play a bit with this. Okay, let me check the time. I should tell you about sample complexity. Oh, can you tell? I cannot change the computer. 20 minutes left. Yeah. Okay. So now the definition of sample complexity. So sample complexity says that is the minimal size of the training set, so that the learner with high probability over the choice of training set outputs a classifier of small risk with high probability. Oh, I already said that. So, how many samples do we need to output a small risk classifier with high probability? And so there are two parameters. There is epsilon, which connects to the risk bound, our goal in terms of risk bound. And delta controls with what probability we want to have a small risk bound. Failure probability of learning. So here is the definition: sample complexity for the hypothesis H with parameters epsilon and delta is equal to the minimum size n of the training set, such that there exists a learner such that probability. Okay, let me make some notation for the risk. So we are given P and a true classifier H, and then I will denote the risk as, so the risk of F as this. And so here is probability over the training set that the risk of the learned classifier is not equal. Should be smaller than delta. Definition in two colors, but that's because the markers are going bad. And another one, but it's red. Okay, so that's sample complexity. Of H. So is the definition clear? We want with small probability that the risk is too large. And we look to the smallest size of the training set, n, here is n, so that the learner can achieve this for all input measures for all true classifiers in the set H. So the learner does not need to output a classifier in H. It can be any classifier. So we allow for improper learning. Okay, so we already said a few things. Sample complexity of H. If H contains two elements that are always different, then sample if H is a singleton, then the sample complexity of epsilon and delta is equal to 0. It doesn't need to see any points to make 0 error. The same is true if H contains two classifiers that always say the opposite label. And now it can be proven that if H contains a point where f of x, so if H contains two classifiers.
For two functions, we need one, not
yeah, sorry, you're right. So if H always contradicts, if two contains two functions always contradicting each other, it's 1. And otherwise, if there is a point where f and g are equal, but also another point where they're different, then the complexity, epsilon delta, is at least logarithm of 1 over delta. So sample complexity is at least logarithm 1 over delta. And that's the same example I already started discussing. So imagine that we have 2 points. F is equal on one point and they're different on the other point. So then I claim even if we set epsilon equal to 1/2, that the sample complexity is at least log 1 over d. Sorry, we need a little bit less than 1/2. 0.49 delta. Let me think. No, it's 1/2. Okay, and so why is it this example works? Okay, I'm not sure. Let's try to prove it with 1/2. Yeah, because here we have at least 1/2. Now in the notes there is a strict inequality, but I will change it because I tried to be consistent with the literature, but I think it's a bad choice. Okay, but most people don't care about these details. So why is this true? Well, we have so let us consider the distribution that gives 1/2 to both points. Imagine that the learner algorithm gets this only copies of this point. Then it doesn't know how to choose between f and g. And so for one of these two functions, it will output the wrong classifier, and this classifier has risk at least 1/2. So for one of the two functions, if we are giving only points, copies of this point, we will have the output. And so the learner has no information of f of g. So for one of these two functions, so if we set h equal to one of these two functions, it will be bigger than 1/2. So you're looking a bit strange. Do I need to repeat something? No, it's okay. Yeah. So what do I claim? So we need to round down.
It's a binary logarithm.
Yeah, binary logarithm. So by default, log equals log 2. No, I mean here in this course, log always needs log 2 and ln is for natural logarithm. It's computer science convention. It's not statistical learning convention, but everyone is from computer science. So me too. So I don't, okay. So that means if we have k, if we have an input of size n, then we always have an error probability, a bad training set, with probability 2 to the minus n. Because that's the probability of picking this point n times. And so that's the distribution that makes this probability big. So for each n, we need to set delta at least 2 to the minus n. And so that gives this bound. Okay. So now, all the previous proofs can be repeated. So here we said if h is finite, then this probability, this error probability was 1 over n. We can apply Markov bound to bound this probability. Okay, so let me first say the claim. And I will skip the proof because I need to speak about threshold functions. And then the lecture is finished. So if h is finite, then sample complexity of epsilon delta is bounded by size of h minus 1 divided by epsilon and delta. And this follows from the Markov bound. Because we spoke about probability over SP and x over p, that fsh of x is not equal to h of x. So this is just expected value of this probability.
Excuse me,
Yeah.
why we have floor here? Maybe same?
Can we do better?
If we
Well, it's when we invert. So when we take n points, we will make a mistake with probability 2 to the minus n. Now if we take delta a little bit bigger, we are good. But if we take delta a little bit bigger, then this becomes smaller. When we take delta bigger, this, yeah, you're good. Yeah, good point. Can do better. So when we take delta a bit bigger, then this becomes smaller, and we're still good. Yeah. Okay, so how do we prove this? Well, we apply Markov inequality. So we view this as random variable. So it's a random variable that depends on S. And now we know that expected value of this random variable is at most 1 over n plus 1. So this is, let us call it random variable. We have expected value of random variable is at most 1 over, size of h divided by n plus 1. And now we know by Markov inequality probability that random variable is bigger than epsilon is bounded by expected value divided by epsilon. N plus 1 divided by epsilon. So how big should n be to make this smaller than delta? So that's what we want. We want this to be smaller than delta. Well, then we flip n plus 1 and delta. So we see that if n plus 1 is bigger than size of, oh, I forgot the minus 1, but it's not so important. So just flip n plus 1 and delta, and we get the lower bound of n. And so if we plug in this bound for n, then we know our algorithm works. But I said I will not prove this, but I just did. What's important is that okay, so for finite classes we are safe. We know the good upper bound. Now also for some infinite classes, they are learnable on average. And they have good bounds on the sample complexity. And we will look at threshold functions on real numbers. So what is this problem? I think we've already spoken about this. So let us define ft of x equal to the sine of x minus t. Okay? And then h is equal to the set of all ft for t and r. And then the bound for sample complexity that we will prove, it's 1 over epsilon ln 1 over delta. So now we have a natural logarithm, and we will need to round up. And note that we have logarithmic dependence on delta. We won't be able to use a leave one out risk bound here. We will use something else. Okay, let us first fix the learner. I need a big picture. Oh, it's 5 more minutes and then we're finished. So we get threshold functions. So that means that there is some true threshold. I will call it t. Above we classify as plus. Here let's classify as -1. And so a training set will contain some pluses, plus ones. I will just write pluses and some minuses. And here is the threshold. So I just told you what is a learning algorithm. It will choose the threshold to be the smallest positive element. So if this is a training set, it will select this point here, let's call it S, and the learner will output Fs. Smallest positive. If there are no positive elements in the training set, he will say all negative function. So we don't need to have that the output of the learner is in the hypothesis class. Okay. And now I need to claim that if we set this equal to n, then the error on the test set, error probability, so the probability that a high risk, that the output that ft is bad, so probability that fs has risk more than epsilon, or at least epsilon, is bounded by delta for this value of the training size. Okay, so how does it work? I will now define some number r, such that this, the probability of this, so probability of RT is exactly equal to epsilon. So imagine that our probability distribution is continuous. For the discrete case, it's a small change, but then it's a bit more difficult because of the small change. So I will explain the simple variant of the proof. So let this be epsilon. So we find this thing. I claim that the only way to output, okay, so by the way, let us first rewrite the risk of Fs. What is the risk of Fs? It is the probability of seeing a point. So negative points are always correctly classified. Fs will say that this is all negative. And he will only start here to say positive. So the place where Fs makes a mistake is between S and T. And so the risk is the probability of the interval St. Okay. So now I claim that if the training set contains a point in the interval RT, sorry, TR I should say, I flipped all intervals. TS, TR, because T is the smallest one. R and S are always above T. So the only way to have a bad classifier is if the training set does not contain an element in the interval RT. If there is no such element, then S will be above this interval. And probability of Ts will be larger than epsilon. And then we have a problem. Will be, well, it will be at least epsilon. So if S is bigger than R, then this risk is at least epsilon. Okay, so now we take n samples and we have to bound the probability that none of them is in the interval tr. So now we select S, x1 till xn, and we select it from Pn. So probability that x1 is not in this critical region. So we will call this critical region, this interval. Probability that it's not in Tr. This probability is exactly equal to 1 minus epsilon by choice of epsilon, right? So that's for the first point. But we are interested in the probability.
X1 not in TR.
Yeah, sorry. Yeah. X1 not in TR and X2 not in TR and so on. Xn not in TR. This probability is equal to, well, all these events are independent, the choice of x1, x2. So this is equal to 1 minus epsilon to the power n. And note that 1 minus epsilon is bounded by exponent of minus epsilon. So the nth power of so this inequality we used many times already. So by checking derivatives. And so this is bounded by exponent of minus n epsilon. Okay, now let us look. We want this to be smaller than delta. This is our question. And the question is, for our choice of n, is it true? So if we solve this for n, if we would set it equal, then we find that n is equal to 1 over epsilon ln delta. 1 over delta. So if we set it equal and we solve, we get this. But the problem is that n is the size of the training set, has to be integer, so we need to round up. And if we make it a bit larger, if we round up, then this is indeed the case. So we have proven this theorem. For the set of threshold functions, sample complexity is 1 over epsilon ln 1 over delta. Okay. So now we know how difficult it is to learn just one real value, that's a threshold. Now you can extend this thing. So imagine we want to learn axis-aligned boxes. So we have, we know that all good values, so we want to learn, okay, we can think about thresholds. Sorry, we can think about finite intervals on the real number. It's the next step. So we want to learn it, so the good values, the positive ones, belong all to some interval. We can apply a similar reasoning, but now we need two critical regions. And so you will do it in the seminar and the homework. And the homework, trapeziums with some fixed edge. And then you can go further and further, but it gets very complicated quickly. And to solve this problem, we use VC dimension. After we know this definition, we never have to think again. We just can check a combinatorial property, and we know the sample complexity up to constant factor. But that's for next lesson. So next lesson, I will prove that sample complexity is equal to 1 over epsilon VC dimension of class H plus ln 1 over delta. Well, that's the result up to constant factor. So there is theta. That's the result, and we can almost prove this. For upper bound, we will have VCH log VCH. So we have this annoying logarithmic factor. But getting rid of it, it's really hard, so we will not prove. It's 2016, it was very recent. So the result we will see next lecture is from 1967 by Vapnik and Chervonenkis, 2 Russians. So their result was ignored for 10 years. I mean, not ignored, but very academic for 10 years. And then, over a long time, it became important. Okay.
Why we used this inequality for extent? We can derive n from previous. No, we have inequality 1 minus epsilon to power n is less than delta. No, the last one.
Yeah.
So
why is it true? Because for the theorem...
I know why it's true. Why we used inequality for extent, we can derive n from this.
So that's the event that we want to know. All endpoints, yeah.
We know that this is less than this.
Yeah,
so
yeah.
we can get n from... No,
we can better, yeah, yeah.
Yes.
Yeah, you're right. And you have better formula, but it's not so nice because it's
yes,
logarithm, yeah.
Yes,
It's a good point, yeah. Okay, that's it. Unless there are more questions. Okay. So, let's do slow.